today. I just want to think about this and how it is going to relate to what we are doing today. So this is just a Riemann sum. 8 partitions. I need to find the region bounded by the graph of f of x equals x squared and the x-axis from 0 to 2. Okay, so we're just going to set it up. For this, we've just got x squared. We're looking from 0 to 2. So right there would have a value of 4. And so if we're going from 0 to 2 and I have 8 partitions, what is the width of each one of my partitions? What? A quarter. All right, so I'm going to take 2. I'm dividing it by 8. That gives me a quarter. That is my width. Okay? And so we'll have here, what we'll have is we're going to have 1/4. If we do a left sum, left, we will have 1/4 times, we'll have, if we're using left, if I think about like my table, it's going to be 0. I'm going up by 0.25, 0.5, 0.75, 1, 1.25, 1.5, 1.75, 2. All right. And if I'm doing a left Riemann sum, I'm not going to use the last one. I'm going to use 0. So I'll have 0 squared plus 0.25 squared plus 0.5 squared plus 0.75 squared plus 1 squared plus 1.25 25 squared plus 1.5 squared plus 1.75 squared. All right, and so I've got 1, 2, 3, 4, 5, 6, 7, 8 different numbers. I used the ones on the left, so I left off that last one. All right, and you could type this into the calculator. It's going to give you your left Riemann sum here, and I don't even think we'll take the time to do that because this is just for setup. If I wanted to do right, what's the only thing that changes? Right, so that 0 squared is coming out because I'm not using that first term. So just let me copy and paste here. So I would be taking, I still have the 1/4. I'm taking out the 0 squared and not using it. And instead, I'm going to use the 2 squared for that. So I wouldn't use that first number. I'd use the last instead, and that would be my right Riemann sum. Okay, so that is our setup. We've got the width of our interval times the function evaluated at all of those intervals. All right, so let's set this up. Using n partitions, find the region bounded by the graph of f of x equals x squared and the x-axis on 0 to 2, use a right Riemann sum. Okay, so it's the same exact problem that I just had, except for it specifically tells me to use a right sum. And this time, how many partitions do I use? I don't know, right? I'm using like a arbitrary amount of partitions. Okay, so it could be 2, or it could be 10, or it could be 25, or 1,000,000. All right, I don't know. So what we are going to do is we need to set it up basically like we did before. We're still looking at that same graph of x squared from 0 to 2. Okay, so the width of each rectangle, which a lot of times they'll call delta x. You're changing x, right? All right. Last time we did 2 divided by 8 because we had the length of this interval is 2 and we had 8 rectangles. So this time my length of my interval is still 2. I got to divide it by n because I don't know what it is. All right? So the width of each interval is going to be 2 over n. So what's going to happen right here, that's at 0. So my next rectangle would be at 2 over n. Where would the next rectangle be? It'd have the same width, right? So if its width is also 2 over n, I'd be doing 2 over n plus 2 over n, which would give me 4 over n. And then 6 over n. And then, you know, that would continue until I got up to 2. Whatever that was. Sure. Made it. Oh, his on-site art drawing is nothing like he thought it was going to be. He's doing it right now, yeah. Because it made it sound like it was show up and draw a picture. He said they give you a prompt. So is he going to have to show up and draw a specific picture that he is not? That's what that sounds like. So all of our practicing for drawing was probably no help. We didn't put that much time into it, but okay. All right. And it looks like a big room with a bunch of kids. So, yeah, so, anyway. Okay, so, back to this problem. All right, so if we think about making ourselves a table, okay, our x and our y here, although we're not really going to worry about it too much. Our intervals would be like 0, and then we'd have 2 over n, and the next one would be 4 over n, and then 6 over n, and then I'm going to put dot, dot, dot here. Eventually, we're going to end up with 2n over n. Right, because 2n over n would give us 2, because this needs to end at 2. Right? So, if we think about setting this up, just like we normally would, the width is 2 over n. And if I am doing a right Riemann sum, which end point am I leaving off? The 0 or the 2n over n? The 0. Alright, so I would start with 2 over n plus 4 over n plus 6 over n plus dot, dot, dot. And then eventually I should end up at 2n over n. And that number right there, like knowing whether or not it's a 2n over n. I'll text it back real quick, sorry. he tends to be a nervous wreck. Like yesterday, whenever we were at I would have been super nervous too. And a lot of the other kids were too. You could tell some of them looked like they were about to throw up whenever they got up there. Like yesterday, Mom, I think I'm supposed to go up there now. Mom, what if they've already called me? I was like, Hunter, there's like 15 dancers in a row here. You're not going yet. You don't need to get up there with all these dancers in sparkly costumes. He gets really nervous. So now he's super duper nervous because his art is not what he thought it was going to be. So yeah, they have to draw it there. But we thought that you've got to draw it there and you just like show up and draw whatever you were going to draw because you have to bring all your own materials. So I don't even know, so.
It's kind of like engineering where they give us a random list of required materials that we don't know until we get there, and then they give us challenges on the spot that we have to do.
So you don't even know the list of things that you're supposed to bring?
Not really.
Well, that's great.
Which, I mean, not there, they're like, you have to use this thing, but they didn't tell us.
Ahead of time that you.
I lied, we got straight to their face and said we had a straw that we didn't have, so they didn't realize.
Yeah.
We also didn't have any Legos, which we were supposed to have, but they were too stupid, lazy to just not see that we had Legos anywhere. So yeah, we had Legos. That's good. It's fine. Ours was definitely the coolest.
Paint something related to somebody that you're up to.
Because we had practiced him drawing this cute little picture, like this, like just with like pencils, like an elk, and it had like the mountains in the background. That was going to be his picture. So I guess what if he's got to do somebody who looks up to him and just draws an elk? Just goes. It's like, this is Bucky the elk, and I look up to him. He inspires me every day. Yeah. Yeah. So, wonder if other kids like knew what they were gonna. They don't tell anybody ahead of time what the prompt is. Okay. All right. Well, because like he likes to draw and stuff, but he's not like. Right. Right. This is not math. You can make it up. You can just come up with crazy nonsense about whatever, even though that yeah. Yeah. Yeah, some art is yeah. Yeah. That is cool whenever they do that. It makes cool patterns. But it's anyway. Okay, we gotta get back to this. Mm-hmm. Yeah. Yeah. Maybe he just keeps texting me. Okay, so.
Oh yeah, this guy not taking melatonin.
Yeah, I forgot my melatonin, and I had severe insomnia, so I stayed awake the entire time we were at the convention.
Woo! I got the entire bed myself.
Oh, man.
Well,
Hunter's not.
It made it harder trying to go to sleep when I had him trying to cuddle with me in his sleep.
Yeah.
Hunter, you bring your
I
bottle.
literally have a picture of him like trying to roll over.
Comfortable. Hunter, you bring your body pillow.
Yeah. Hunter's probably not gonna sleep either. There's gonna be 4 6th grade boys in a room with no supervision.
It's like a giant shark.
Yeah. Yeah. I told him about the doors taping. I'm not 100% sure if they're taping doors, but surely they're taping doors. So I've told him they're taping doors, even if they don't tape doors. I'm hoping he thinks they've taped the doors. Surely they're taping the doors.
I didn't care that
Yeah.
the door. I just opened it anyway.
Yeah, so, gosh, if they call me and they found Hunter over at the mall or something. So, yeah. Okay. All right, so let's look at this. What we've got to do here is we've got to turn this into a summation. Because if we can turn this into a summation, then we're going to be able to do a limit as n approaches infinity. Because if we have infinite n's, infinite bars, right, because that n is the width of your bar, or the number of the bars. 2 over n is the width of our bar. Still takes me. It's telling me all about it instead of drawing, I think. Apparently. Yeah. 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 Let's yeah, I'm going to ask him. Let's see what it is. Please be something about nature. Then he can draw the elk that we've practiced. Otherwise, who knows what it's going to be. Yeah. I'm pretty sure if he's got to draw a person, this may not go well.
I know somebody in our group, she drew, she painted like New York, specifically like the Empire State Building, because she said it was related to her sister who was a big artist, and she wore something. She was like, she plays.
Right. Right. Art, you can just make something up about anything.
Art is abstract.
Yeah. It's about how you feel inside.
So, Hunter, how do you put on elk?
Yeah. Yeah.
Right?
So, yeah, right. Yeah.
Don't let your antlers decide who you are.
Yeah. Like, yeah. I don't know if he's got that in him. I don't know if he understands the just making stuff up and making it sound good. I don't know if he's, yeah. Maybe he'll text me about it and I'll tell him, still draw the elk, say this. All right. Okay, let's look at this. We need to turn this into a summation. All right, so this 2 over n, we can put inside or outside of our summation. It really does not matter. I'm going to put it on the outside. We want our index to be 1 because we do not have shortcut rules for anything else. And we want this to go to n. So, the question is, how do we write what we're seeing here as a summation? Okay, we need an I. The I needs to go wherever we're seeing a number change, right? So we did some of these on that homework where you had to write a summation for a sequence. But I has to go up by integers. So I has to go up by 1, 2, 3, 4, 5. What do we see happening here? 2, 4, 6, 2n. So we can't, there's nothing where we can say like, this is going to be I, but skip a number. Right? We can't do that. So how can we do that mathematically where it'll work out like that? We do 2i, right? So if we make this 2i over n, like that, let's test it. Let's make sure that's going to work. If we plugged in 1, we'd get 2 times 1 over n, which would be 2 over n, right? If we plug in 2, 2 times 2 over n, which would be 4 over n. And then 3, 2 times 3 over n, which would be 6 over n. So if we need to skip numbers, we can, if we're skipping every other number, we can do that by just putting a 2 right there. And then all the way up to, eventually you would be plugging in n, so you'd have 2n over n, which would be that last thing that we need right there. That'd give us 2, right? So this will work. So we've written this as a summation. Okay. So this is where we're going with this. This particular one doesn't ask us to find an answer. right? I think I'm going to on the next one. Hopefully the same question. Well, I got to do that first. Oh, I didn't. Okay. Actually, let's just go ahead with this one while we're at it. Okay, so if I have this, I've got this set up with the eyes. Now, if n is my number of rectangles, if it equals infinity, then I get the exact answer, right? So I can write this as the limit as n approaches infinity of 2 over n times the sum of I equals 1 to the n of 2i over n. Now, I don't know how to do a limit of a sum, but I do know shortcut rules for this sum, where I can get rid of the sum notation, right? So, if we put together what we've learned, the shortcut rule here, this is an n, which is not an I, right? So it can be pulled out. So I could pull it out. It would go over here with the n that's already on the outside. Okay? So that would look like this. Limit as n approaches infinity of 2 over n squared times the sum from 1 to n. Actually, in fact, this 2 right here, I could pull it out too, because it's just a coefficient. It really doesn't matter whether you pull it out here or pull it out later. I'm going to go ahead and take it out. So that would make this 4 right here. And then I would have just the I right there. What is my shortcut rule for the I? That is for the coefficient. So if it is like 1 or 7 or 15, then it would be like 7 times n. For I, it is n times n plus 1 over 2. Which I can distribute here. So I have limit as n approaches infinity of 4 over n squared times n squared plus n over 2. And if I multiply those together, you can reduce the 4 and the 2 if you want, or you can leave it like it is. It really doesn't matter. I think I'll just leave it like it is. 4n squared plus 4n over 2n squared. And what you should see if you have done this correctly is you should end up with the same exponent on the top and the bottom. Your highest exponent on top and the bottom should be the same. So what do we do to figure out this limit right here? What? No, and it's going to be what? 2. Right? Just divide your coefficients. 4 over 2 is going to give you 2 for that. All right. So that's the exact area. It's a long ways to get there, right? But that gives you the exact area. So we're not going to do a lot of this. We're going to do a few problems like this. But this would be, starting, this sort of takes you through the minds of like the people that were developing calculus here. They started with these rectangles, and they were just doing like 4 rectangles, and it was like, this is not great, so let's do some more rectangles. And then they started thinking, well, what if there were infinite rectangles? And so in order for there to be infinite rectangles, you've got to have all this summation, and then you got to have shortcuts, you got to take limits. You can get the exact answer. Okay, so they were working on this to develop parts of calculus that they really didn't even realize was calculus yet. Our area formula is going to be our limit as n approaches infinity of, I usually put this delta x, I usually put it over here instead, but our formula in the book did not. It's the sum from 1 to n of f of the ci, that's just your index, however you need to do it. In the case of the one we just did, it was 2I over n. And then we pull that out there. So your interval is always the length of your interval divided by n. So like on that one, we were going from 0 to 2, and we divided that by n. So we had 2 over n. If we were going from 0 to 10, we do 10 over n as our length of our interval. I'm not going to give you anything that doesn't start at 0. All of the ones I'm going to give you are going to start at 0, because if they don't start at 0, it makes it a lot harder to set up. And we don't need to spend time on that because it's not something you're really going to see, I don't think. So let's look at the next. Oh, did I do this last problem wrong? I did the last problem wrong. Here's why I did it wrong. Okay, I did this wrong because 2 over n is not this plugged into the equation. What should I have done to my 2 over n? I should have squared it. Because you got to plug, like, when we have those numbers, when we have 1 and 0.25, like on this one we were doing right here, see how I squared each one of these? I failed to do that over here. So, instead of going back and redoing the problem, because we do not want to go back and redo that, let's make this the function f of x equals x, and then it works. I should have squared each one of those, which means instead of having 2I over n, I would have had 2I over n squared, which would change my problem a little bit, but we'll just see on the next one what we've got to do there. So, area of the region between the graph of the function and 4x plus 2 and the x-axis over the interval from 0 to 4. Okay, so I like to try to set up my summation first, and then you got to do that limit as n approaches infinity. So if we think about this, what is my delta x, or my width of my rectangles here? 4 over n. Okay, and what I did wrong on that last one is I wasn't plugging those values into my function. So like my table would look like this. I would start at 0. My next interval would be at 4 over n. What would the next one be at? It'll be at 8 over n, and then 12 over n, and then it'll continue dot 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 until you get, where would you end at? To get 4, what would you have to have? 4n over n. Like that. So what it's going to look like here is we'll have 4 over n times, and then you're doing, I'm going to write it this way so I don't forget. We'll have f of 4 over n plus f of 8 over n plus f of 12 over n plus dot 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 plus f of 4 n over n. Right? Which plugged into the function that we're given, our f of x right here, is going to look like this. I got 4 times 4 over n plus 2 plus 4 times 8 over n plus 2 plus 4 times 12 over n plus 2 plus dot 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 plus 4 times 4n over n plus 2. So I'm just plugging these values here into whatever the function is. In this case, it's 4x plus 2. So if I'm trying to write this with a summation, I need to look at what's changing. So we can see this value is what's changing each time. So the 4 over n, you can write it out front. And then we're going to have a summation from 1 to n. And so my formula, the 4, the n on the bottom here, and the 2 is all the same. So I'm going to use those for my formula. What do I have to use right here in this spot where that I need an I there? But if I put I, it's going to go up 1, 2, 3, 4, 5, 6. And I need it to go 4, 8, 12, and so on. So what do I need to put with my I? 4I. We're okay here. Does this make sense what we've done? Okay, so this 4 over n is just going to stay out front for a while here. I'm going to go ahead, I'm going to make that over 1. I'm going to make this 16i over n plus 2. Be careful here. Can you pull the n out on this one like we did on the last problem? Does the 2 have an n with it? It does not, so you want to leave it where it's at on this one. If both of those were over n, then you can pull an n out, but they're not in this case. So, so what we want to do is we want to use shortcut rules. And so our shortcut rule for I is n times n plus 1 over 2. So we're going to have the 16 and the n stay where they're at, and it's going to be multiplied by n times n plus 1 over 2. So these two pieces right here, the 16 and the n, that's where they go. And then this part is our shortcut rule for the I, for the sum from 1 to n of I. Then we also have to do the shortcut rule for that 2. So if I'm doing the sum from 1 to n of 2, just the number 2, what do I get over here? 2n. And at any point here, you could put the limit. I'm going to wait just so I don't have to write the limit notation every time. So this is going to be, if we take like this 16n and distribute here, we'll get 16n squared plus 16n over 2n plus 2n. And then it's really up, what I would probably do, I think the easiest way to do this is going to be to distribute that 4 over n to both terms. And the other option is to try to get common denominators here and put it all together as one fraction. But what I'll have here, if I distribute here, 4 times 16 is going to be 64, so I'll have 64n squared plus 64n over 2n squared plus 8n over n. Because that 2n is over 1 there. Okay, here, the algebra gets a little... Alright, so we need to do the limit as n approaches infinity of this stuff. And I could get common denominators and put this all together, or I can just do the limit as n approaches infinity of 64n squared plus 64n over 2n squared plus the limit as n approaches infinity of 8n over n. You don't necessarily have to write that step. I just want you to see what I'm doing here. So this is going to be limit as n approaches infinity of 64n squared over 2n squared. We're going to divide our coefficients. We'll get 32 right here. And what will we get for the second part? 8. And we'll get 40 overall for that. Okay, questions? So whenever you're doing a limit of two, like, things that are added together, you can just do the limit of each one of those separately and then add those answers together. So if I do the limit of this first part, then you're just doing Bobo-Botno, exponents are the same, divide your coefficients, so 64 divided by 2 is 32. And then the limit of the second part, exponents are the same, divide coefficients, you'll get 8 for that. And then you'll add those together. The other option is to get common denominators here, but this is a little bit quicker to do than to try to get the common denominators for that, because you could like multiply this by n on the top and bottom and put them all together, but that takes a little bit longer. Okay, definite integral notation, just real quick. Whenever you see this, I've already alluded to this, but when you see this expression, the area, this means the area under the curve f of x on the interval from a to b. We call a your lower limit of integration. B is your upper limit of integration. And then f of x, of course, is just your function for that. So our book is going to use this notation some and ask you to find the exact area. I want you doing limit definition right now. I'm not going to give you many of these. So what it'll look like in your book, you will have one of these. So I need to tell you real quick what to do with this. I have not taught you how to set it up unless it starts at 0. Because if it starts at -1, that makes it much more complicated to set up. So, something like 1 minus x squared, what does it look like? It's a parabola. Is it smiley face or upside down? Upside down, it's going to cross right there at 1. What do you know about this particular graph? Particularly the sides of the graph? It's symmetrical. So if I find this area right here, I could just double it, right? So what you're going to have to do is just going to be 2 times the integral from 0 to 1 of 1 minus x squared, like that. So you would be setting up, like, the length of this interval is 1 over n, and then you have like 1 minus 1 over n squared plus 1 minus 2 over n squared. Yeah, it's inside of, it's just squaring that 1 over n. And then 1 minus 3 over n squared plus dot, dot, dot there. So what do we see changing in our formula? Just that numerator there. So when you write it, you're going to get 1 over n, the sum from 1 minus I over n squared. This time I am just going to use an I because it's not skipping. It's not going up by 2s or 4s. Like that. Oh, and I should put from 1 to n. So then, real quick, this is going to be the sum from, I realize we're about out of time, of 1 minus I squared over N squared. And then you're going to use shortcut rules. So this is just going to be 1 times N. And then this is going to be your I squared rule, which is like, gosh, N times N plus 1 times 2, N minus 1. Is that it? Over 6. And then I'm going to just write that 1 over N squared out front of it. And so you would be doing the limit as N approaches infinity of that. Do your best on setting up this homework here. Don't stress too much if you're struggling a little bit with it, because it's mostly like the understanding of what's happening that I want you to know. But try to at least set something up for each one.